Okay, guys, this title of section 4.2 is the mean value theorem. Okay, the mean value theorem. So all I want to do today is just have you guys look over these graphs and try to understand what the mean value theorem would state. Okay, so the instructions were, you got 5 graphs here, 6 actually, and you're supposed to connect a secant line from AF of A to BF of B. I assume everybody did that correctly. So let's do red tangent line, or red secant lines. Okay, so you would be going from here to here. Did everyone draw that? Okay, from here to here, from here to here, from here to here, from here to here, and from here to here. How many of you got that part right? All right, good. So you know what a secant line is. This is the answer for part A. Okay, the second question is a little trickier. The second question is asking, determine how many tangent lines to f of x are parallel to the secant line you drew in A. Okay, so I'm referring to, I should have typed this. Let me type it in now. We're supposed to stay in the interval AB. Okay, so just stay in the interval. Don't try to race off the other parts of the graph. I kind of cut these off anyway. But what about tangent lines? What would those look like? So let's do that in green. So we know that there are many tangent lines to a curve, right? Do you think any of those might be parallel to the red line? That's the question. It's a little hard to tell if it's 1 or 2. So let me re-sketch my curve. So my curve goes, the way I drew this curve, it basically was on the rise at the beginning, and it went up like that. So there's only one, I believe, right here. This is the only tangent line that is parallel to A, line A. So that says B, one answer. Okay, let's look at the second graph. So if you sketch in tangent lines here, these are all on the rise, and then we hit this sharp corner type thing here. Might even be a cusp, hard to tell. This then produces these tangent lines for this other piece. Are any of those parallel to A? No, I don't believe any of those are parallel to A. So this one is none for part B. Okay, how about this third one? Our tangent lines get steeper and steeper and steeper on this side, and then coming to the right side of the asymptote, these slopes are getting less and less steep. Are any of these green hash marks parallel to that red line? No. Okay, so probably a none on this as well. All right, let's go to this next diagram. Here we have a true corner, so these tangent lines actually hug the curve. So all of the tangent lines to the left of the corner are right on the black curve. And then there's an abrupt change in slope, and the rest are like that. In fact, you could probably say that since this is linear, these are all slope 1, and these are all slope -3/2 or something. You say all of them. So do you think any of them have the slope of that red line? No. Again, a none. Okay, none again for B. Okay, in our next drawing, the tangent lines right here are of course hugging the line. So none of those are parallel to the red. But up in this region, we might have one right here. One and only one where it's parallel. How many of you answered 1 for that 5th drawing? Good job. And the last one, I count 3. Do you guys see them? This one, and this one. Anyone else have those? Yeah, 2. 2 of them? Did you have the top 2? Okay, so I guess we're trying to come up with a new rule. Like, when will there be such green lines like these? And when will there not be green lines like these? Okay? So back through this, and let's look at all the ones where we failed to find a green line. And let's see what those graphs have in common. Okay? So this was a failure, right? Sorry, you were drinking. Okay, I did. Right. This is a failure, right? This is a failure. Those are my three failures. What do they have in common?
They're not differentiable.
Okay, yeah, this one with the cost sort of thing, that's not differentiable at an interior point. This one, vertical asymptote. Now, does that mean it's not continuous or not differentiable?
Not continuous and not differentiable.
Both, right? It's both. It's not continuous and not differentiable at this value of x between a and b. Here we have a what? Corner on an interior point. So it seems like we might be able to say something like, if there is a discontinuity or a non-differentiability or something, then we definitely will not have one. But then this down here defies that. Let's look at this picture. In this problem, we have a jump discontinuity. Those are really not even fixable. Horrible jump right there. And yet we still have a tangent line that's parallel to the red. I don't think we'll be able to say that if there's a non-differentiable point, then there's no tangent line. See what I'm saying? That's parallel to the secant. Okay, so let me ask it this way. Let me flip the question around. When will we definitely have a tangent line parallel to the red line? Let me ask it that way. Under what conditions? What? When there's a local maximum in. Okay, that seems like a pretty strong argument. This graph had a local max right here, and we did get one. This has a local max, but it didn't work. So that's not a good answer. It's not a complete truth, you know. What's
As
that?
long as it's both differentiable and continuous, then we can be assured that there will be a tangent line parallel to the secant line of A and B.
Yes. Okay, so the way this theorem works is this. As long as the curve is completely connected and completely smooth from A to B, right, then we will definitely be able to find one of these green lines. Okay? If there's a break in the graph or a sharp turn in the graph, we cannot guarantee that. We can't guarantee that we'll have a green line, such as this one in A, in this first drawing. So this is what we call our second existence theorem. And it's worded like this. It's called the Mean Value Theorem. And here's how you would probably write it out as a sentence. If f of x is continuous on the entire interval, start to finish, you could draw the whole thing without lifting your pen. And that's true for most of these graphs, not all of them. And here's your second condition. F of x is differentiable at least on the interior. So this is open interval AB. Then there exists at least one point, I should put one value of x on the interval from A to B such that f prime at that value, we'll call it one value of x, we'll call it c, we'll call that value c, okay? F prime at c is f of b minus f of a over b minus a. This is just basically saying that the slope of the tangent line, also known as f prime c, is equal to the average rate of change across the entire interval. That's the same thing as saying the slope of the red line. In other words, there is a spot somewhere on the graph where IROC equals AROC. IROC equals AROC somewhere inside that interval. But it only is true for graphs that are continuous and differentiable. All right. So we're going to stop there today.